Okay. So far what we know is that we know about convexity, we know about subgradients. There is one thing which I forgot to mention about subgradients and which I was reminded during the break, is that there is a very peculiar property of subgradients, which is that the set of all subgradients at any point is always a convex set. You may have guessed it, but the set of subgradients is always convex. Okay? This is again a remarkable property. Okay. So now, it's not obvious, but it's a remarkable property. Yeah.
Some subgradients will only exist for convex functions.
Yeah. So this notion of subgradients may not exist for other functions which are not convex. So there may be, but for a convex function, you can be assured that there is always a subgradient. The definition, of course, doesn't have anything to do with convexity, but the fact that it exists is special only for convex functions.
So at an inflection point, you don't have one, right? If it's like if you have the cubic.
Yeah, if it is non-convex, then it may not exist. There may be no subgradient. But for a convex function, you always know that there is a subgradient. Okay. So now let's do sort of two warm-up exercises. Right? So the first warm-up exercise that I want to do is to show you. Okay, so now you know all about convexity. You're all gung-ho, and you want to go and try minimizing. I mean, doing some real code, right? I mean, so some of you must be getting really antsy and say, "Show me code, show me code. Tell me how am I going to do stuff?" Okay, so let's do stuff. So what am I going to do is let's try and minimize a one-dimensional convex function. This is sort of a nice exercise and gives you many insights about what you can do. So the task is sort of clear, and this is usually how you specify the problem in optimization as well, that I give you a function. Okay, the function is some black box. The only thing I tell you about the function are two pieces of information. I tell you that the function is convex and it is smooth. Okay, so these are two pieces of information that I give you. And I also tell you that, oh, here is some black box. There is a black box or an oracle if you want. You can go and ask the oracle, you feed it any location x, and you can say, tell me what is the value of the function at that location x, and the oracle will come back with an answer with a real number. And you can give it some x, and you can say, find me the gradient of this function at that location, and it will come back with a number. Right? So this is the two things that the oracle can do for you, and you know that the function that you're dealing with is convex and smooth. Okay, problem clear? Okay, and your job is to locate this red point, right? So this minimum point of this function. Yeah, this is your job. So how are we going to do this? Before we do this, let's do a little bit of math. Right? It's inevitable. So let's look at this first order condition. Right? So we knew this first order conditions from before. We know that the gradient satisfies this property. And now let's just switch w and w prime. Oh, one important notation thing that I want to talk about. So when I'm talking about general convex functions, more or less I use the function, I call the function f for g or some small lowercase letter. When I'm talking about optimization, or whenever I'm talking about minimizing something, I use uppercase j and nabla j and j prime and so on. So whenever you see j, sort of keep it at the back of your mind that there is some function which you are trying to minimize. Okay, so just so that you know this. Okay. And also I switch to the w because that's my parameter usually. Okay. So now I can take my first order conditions, I can switch w and w prime, I can rewrite it, and I get this. Okay. So this is I mean, while this equation looks ugly, what does this tell you? The equation sort of tells you that if w is larger than w prime, then the gradient of w must necessarily be larger than w prime. Right? What is a function which satisfies this condition? It's a monotonic function, right? Which means when, so if I give you, it's a function which is always non-decreasing. Okay, so if I go along the w axis, the function always is non-decreasing. Right? So now what we have figured out is for a one dimension. Okay, so this is very special. Again, I want to remind you, this is very special. This holds only for a one-dimensional function. This does not hold in general. You can make a equivalent but not exactly the same, because there is no notion of monotonicity in n dimensions. So you cannot make this statement in n dimensions, but in one dimension you can always make this statement, okay, that the gradient of a convex function is an increasing function. Right? Again, one of these remarkable properties that follows from a very local condition that you enforce on the function. So let's take a function like this. If you take the function like this and if you plot its gradient, the gradient looks like so. Okay, so it's always an increasing function. Okay. If you take a function like this, which is also a valid convex function, okay, the gradient looks like so. Okay. And remember, sort of you can already see this. Wherever the function attains its minimum, these are all the points where the function attains its minimum, the gradient actually is 0. Okay. Clear? So now you can sort of reformulate, now that you have this new intuition about, oh, the function is, if the function is a non-decreasing function, then, and on top of that you also know from sort of before the break that all you really need to find out for a convex function to find its minimum is to locate the point where the gradient vanishes. Right? So you remember the first order condition. So you want to find a point where the function vanishes. So which means that you can restate this problem as I give you a non-decreasing function and you want to find out where the function crosses 0. Clear? If I gave you this problem, any ideas on how you try to solve it? Don't cheat and look at the slides. So if I gave you a monotone function, a function which is non-decreasing, which is, say, let's make it simple. Let's say I give you an increasing function, right? So you know that the function always increases. And I told you, find me the point where it crosses 0. So even before that, a simple question. Can an increasing function cross 0 at more than one point? Never. Right? So there's exactly one point where it crosses 0, right? Where the function is value 0. So now I give you an increasing function and tell you, find me that point. How would you go around trying to find that point? Wild guesses? Binary search, right? So you do a bisection. That's exactly what we are going to do. Here is how we do it. Right? So let us say we start with some lower bound and some upper bound. So somebody tells you, this L is some lower bound and U is an upper bound, and this interval, this red interval that I show you is sort of our interval of uncertainty. Okay? So we know that at L the gradient is negative, at U the gradient is positive. So clearly we know that somewhere between L and U the function must cross 0. Right? All we don't know is where does it cross 0. So this is sort of our interval of uncertainty. So what we do is at every point this is a very dumb and naive algorithm, but sort of gives you a flavor for what you can do. What this algorithm does is it finds the midpoint. Okay? At the midpoint it will evaluate the gradient. So remember, we always have our black box available to us. So it goes to the black box and asks for the gradient at this midpoint. If the gradient happens to be positive, you simply move the upper on location up to here. Okay? Then again you do the same thing, you find the midpoint. Okay? If the gradient there happens to be negative, which is the case here, you move the lower boundary. And you keep doing this until you have localized this interval to a very small value. Right? Here is the entire algorithm. Okay, and there is a condition which is basically a numerical tolerance which tells you when you should stop. Okay, and otherwise it does exactly what we talked about. So it takes the middle value, if the gradient is bigger than 0, then it sets the u to m, otherwise it sets L to m, and then at the end of it, it just gives you the midpoint of whatever is the interval left behind. Okay? And this is a complete algorithm. You can code it up. You can show that it converges pretty fast. It converges in log. So if you want to get an epsilon precision, you can get it in log 1 or epsilon iterations. Okay? So if you just did this, if you went into this loop log 1 or epsilon times, you would get a solution which is epsilon precise. Okay? And you can do, of course, more fancier things. For instance, you could do Newton's method, which is uses the slope of the increasing function and does more fancy things with it. But just as a warm up, I just want to show you how easy or how benign it is to find the minimum of a one-dimensional convex function. Right? So this is something that you could just write code today and do it. Okay. Now, questions? Yep. Yeah, sure. Yeah, 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 yeah. Good point. Yeah, it's not necessary that the function has to be strictly increasing. All you need is some sort of continuity of the function. Okay. Questions, comments, others? Good. Okay. So now let us do some sort of slightly more fancier algorithms, right, or slightly more fancier algorithms. And as I'll show you, many machine learning algorithms, and some of which you may have used in your research, actually do this. Okay, and that's sort of what I'm going to show. So let's formulate the problem like before. Our problem is that you're given a black box as before. You know that you want to minimize a function. Now the function is an n-dimensional function. Okay. And you can compute its gradient. So the black box can compute the function value, and it can compute its gradient. And you're also told that the function is smooth and convex. Right? So exactly the same setting as before, except that now your function is n-dimensional, and the gradient, of course, is an n-dimensional map. Okay, clear? Good. So let's make it more concrete. Just because I wanted to show you this and really visualize this for you, because this is many books talk about it, but I think a picture speaks more than 1,000 words. So let's take a quadratic function. So you can verify that this function is actually a convex function. Okay, and this is the contour of the function. Okay, so here is the simplest, potentially the stupidest idea that you can think about. So well, this is a two-dimensional function, right? So it has x and y. Okay, so this is x and y. Okay, and then there is the value of the function. So you say, well, let's do the following thing. Let's start by fixing y to be at 3. Okay, so let's start from some random point. So the random point I choose is that y equals 3. I fix y equals 3. Okay, and I look at this function, which is f of x with y fixed at 3. Okay, so this is this function, which I can rewrite as follows. Right? So I can rewrite this function in this way. Okay? And what I'm doing now, if you think about it, by fixing my y to be 3, what am I doing? I'm slicing the function. Okay? So it's like, again, the same, remember your meat slicer. So you bring the meat slicer out, and instead of slicing it horizontally, you're slicing it vertically. Right? So you're slicing the function at that location. So it's like you take a slicer, you slice through it. And I look at how the function looks like. Okay? This is how the function looks like. Everybody clear what this operation is? What the slicing is doing? Okay? So this is slicing the function along the y-axis at y equals 3. Okay? I get a function which is a quadratic. Okay? I mean, you don't really need all this convex analysis or all that what you learned today to minimize a function like this, but I just assume that you know how to minimize a quadratic. Do a little bit of back of the envelope calculation, and you can show that the quadratic attains its minimum at this value, right? some 0.45 or something. So that's the value there. Okay. So now what I'm going to do is I'm going to go back to my function, fix my x at -9/20, and slice the function again. Okay, now this is actually this is a bad visualization, but actually I'm just trying to show you that you're trying to slice the function at minus 9 by 20. Okay, so you slice the function, and what happens? You get another function, which of course also happens to be quadratic. So this is not, you have to remember, this is not an accident that every time you slice, you get a convex function out of it. Remember I told you this, projection along any direction is convex. So which means that every time you slice along a coordinate, you'll always get a convex function. In this case, actually you get more than a convex function, you just get a quadratic function because the original function was quadratic. So I fix my x at minus 9 by 20, I get a quadratic in y. Okay. Again, I can find the minimum of this quadratic. This is whatever 27 by 40, and I plug it in. Okay. And here is what it looks like if I slice again along the x direction at 27 by 40. Okay. Sorry, along the y direction at 27 by 40. Are we done? So what did I do? I sliced the function along one axis, I kept my y fixed, I found the minimum. Okay? Then I kept my x fixed and found the minimum. Okay? The function has two coordinates. So I optimized along one coordinate and then I optimized along the second coordinate. Should I go home? No? Don't want me to go home? You want me to stay on? In fact, you are not done. If you look at where you are in the x-axis, you are here, right? While the actual true optimum is somewhere there. So what you need to do is you need to repeat this procedure many times. So you want to fix your x, optimize along y. Keep your y fixed, optimize along x. Then keep your x fixed, optimize along y. And keep doing this multiple times until you find the minimum. At the minimum, if you optimize along x, you'll remain where you are. If you optimize along y, you'll remain where you are. Okay? This is coordinate descent.
Does it guarantee convergence?
Yes, but very, very slowly. It depends. That's exactly where you need to know more about the function that you're optimizing. So if you knew that your function was strongly convex, for instance, you can make better statements about how fast you'll converge. But if you just knew that the function is just convex, it may be very slow convergence. It may be painfully slow convergence in some cases.
What's the worst case performance?
Worst case, you could just you could have exponentially bad convergence. But if you're strong, so if your gradient is Lipschitz continuous and it has, I think it's more than probably it's twice differentiable, then you can say something about you'd get dimension cubed times log 1 over epsilon rates of convergence. That's basically what you get. Okay. So is coordinate descent clear to everybody? You just take each coordinate at a time, you optimize, you know how to optimize a one-dimensional function, so you're pretty much in good shape. Okay. Questions? Okay, so let's switch to the second talk. Okay, so keep this really simple algorithm in mind, and we will talk about it in the rest of the lectures. Okay, so that was the end of sort of giving you insights into convexity. Again, I'm only scratching the surface, really only showing you very crude things that I know of. I'm sure there are more sophisticated things out there and also more precise statements that you can make, but I thought instead of trying to get those precise statements across, which at 8:30 in the morning I'm sure nobody remembers, hopefully some of the pretty pictures stick with you. Now we're going to switch gears and get into sort of the meat of what I want to talk about, which is basically optimization for machine learning. Okay, so how do you build optimizers for machine learning? After all, all of you are working on some aspects of machine learning, and more or less you build models, and at some point you would have to find an optimizer for your particular task. Okay, So what I'm going to show you today, and this is going to be my prototypical example all the time, is support vector machines. Okay, so I'm just going to talk about very briefly about what support vector machines are and what the optimization problem is, and then we will look at various strategies on how you can develop optimizers for SVMs. Okay, so that's the plan for the rest of the 3 hours. Okay. So let's talk about simple binary classification. Again, many of what things that I'm talking about can be extended to other fancier settings. So for instance, you can do multi-class, multi-label, structured prediction. All of these, the underlying principles in terms of optimization are more or less the same, right? So that's why instead of showing you this variety of models, which I'm sure all the other, like you got a lot of it from Dale's classes, and you'll also see in other classes, I want to focus on the underlying optimization problem, right? So for that, this is sufficient. So the prototypical example in machine learning, you're given a bunch of blue circles and red diamonds, and you want to build a classifier which will detect or which will separate the blue circles from the red diamonds. Okay. So there are clearly this data is linearly separable. Okay. So which means that there is a linear hyperplane which separates these points. And there are of course a number of linear hyperplanes, actually infinitely many linear hyperplanes which can separate this data. And from among them you want to choose a good one. And how do I measure what is a good one? I measure this by this notion which is called margin. Okay, so the margin simply says that among all hyperplanes, so if this is the hyperplane, this is sort of the level of uncertainty that I have about the hyperplane. Okay, and then the principle of margin maximization is simply saying find for me the hyperplane which has the largest margin, in other words which is the most uncertain about your data. Okay, so this is a simple geometric thinking here. And again, this is by now fairly standard, you almost see this in undergrad classes, but just to remind you, you can set this up as an optimization problem. So the way you set this up as an optimization problem is you say that I'm going to write this hyperplane, the equation of this hyperplane as Wx plus b equals 0. So that's going to be my equation of the hyperplane. Okay. There is a scaling effect that happens. To fix the scaling, I'm going to assume that the closest point, the hyperplane which passes through the closest 2 points can be written as Wx plus b equals plus 1 and Wx plus b equals minus 1. So there's a scaling effect that you have to take into account. And once you write this, you can do a little bit of simple algebra and figure out that the margin is nothing but 2 over the norm of W. Okay, so if you want to maximize the margin, you want to maximize this quantity 2 over norm of W. Okay, subject to the constraints of course that all the points here are on the right side of the margin and all the points here are on the right side of the margin. Okay, again this is something that's fairly standard. I'm going over it really fast. It's just meant to be a reminder, not a course on SVMs. Okay, so if some of it is not clear to you or you are not familiar with support vector machines by now, please come and talk to me. Okay, and I can do this in lot more detail. And you can set up an optimization problem where you introduce some sort of a slack variable. So the slack variables are to say, okay, if a point doesn't quite lie on the right side of the hyperplane, then how are you going to penalize it? There is a linear penalty that we apply, and this is what the optimization problem comes to look like. Okay, so while this is all sort of geometry that was used to derive, let us massage this thing a little bit. Okay, so let's try to get this into some form that looks more familiar and more reasonable, right? So you sort of said, oh, you introduced the geometry, and then Dale told me, oh, you should actually use a regularizer and a loss function. Where is your loss? What is the proxy? What's going on? Okay, so let's connect the two things up. Okay, turns out they are both closely and intimately related. If you do a little bit of transformation, right? So if you realize that psi I is always bigger than 0 and psi I is bigger than 1 minus yi w dot xi plus b, right? So if you put these two facts together, you can eliminate the psi I and you can write your objective function like this. Okay. Now things start becoming reasonable. You see, you can you can look at this. This is nothing but lambda times the regularizer. In this case, you are using the square norm regularizer. Okay. So using the square norm regularizer, and this 1 over m summation is nothing but the empirical risk. Remember, we had this formulation we started with. We said a number of machine learning problems can be written in this way. So I am just showing you one example of how a standard problem that you may have seen before, which is the S.V.N. problem, can be written in this way. Okay. So there is the empirical risk and the regularizer, and the parameter lambda trades off between the two. Okay. Now you can, this is a problem I write with the bias B. Sometimes you also want to solve it without the bias B, but it does not matter. We will see some subtle differences between the two as the lecture goes along. Pay attention to that one, to the bias. I will point it out. But more importantly, for now, if all of that zipped past you, do not worry. Just concentrate on this one and follow along. Okay, so this is the time to come back. If you are doing Facebook and Google and whatever, come back. Okay, this is the time. So what you need to pay attention to is that this is a problem which is unconstrained, which means there is no constraints on any of your variables. Your variables can take on any value. It is non-smooth. Can somebody tell me why is it non-smooth? Sorry? Yes, the hinge loss, right? Because of the max. Okay, good. And of course, it's convex. So you can verify that it is convex because this is piecewise linear. Summation is convexity preserving. Quadratic is convex. Summation is convex. Right? So it's very easy to verify that it's unconstrained, non-smooth, and convex. So now we want to design optimizers for solving this. Okay? And of course, non-smoothness is one of the issues that we have to tackle. And now let us sort of, what I am going to do now is show you a few different optimizers and show you how they are all connected and what's the relationship between them. Here is sort of the simplest optimizer that you can code up. Literally 5 lines of code in Python or MATLAB, right? Which is, this is an optimizer which does what is called stochastic gradient descent. Well, again, don't worry about the exact algorithm. We'll dissect it in great detail next. Okay, but I just want to point out basically what it does. It has a current. It starts with a weight vector W0. At every iteration, it has this thing eta t, which we will call the step size. Okay, so it has what is called a step size. It checks whether on the current data point is your prediction correct, right? If a prediction less than, if it is less than 1, so which means you are making some sort of an error, then there is a certain update that is done to the weight vector, and if you get it right, then there is a certain other update that is done to the weight vector, right? And then once you get this weight vector, you sort of do the norm, you take its norm and somehow shrink the norm. Okay, so this is the shrinking of the norm. And that's how you get your next weight vector. So the setting that you should keep in mind for this particular algorithm is that think of you have your data, you take one data at a time. So you take one data point at a time. Okay, you do a simple check using your current weight vector, and based on what that check returns, you either do one update or you do another update. Okay, so clear? So I'm just assuming that you're going from t equals 1 to t, and xt is the point that you see at time t. Yeah, t is the number of samples.
So the stochastic come from the order of elements?
Yes, so we will dissect this algorithm in great detail. Just hold on for just a minute. It is very similar to a perceptron algorithm. It's more or less a perceptron with a margin. I mean, there is a margin term here, but it's more or less a perceptron with a margin. Okay. The eta t rate is set so that you get the right rates of convergence.
It is just predefined and it remains.
Yes, it remains the same, and that's actually one of the problems with this when you implement it in practice. But it is so there is a great debate in machine learning about how should this eta t be chosen. So Leon Boutou, in his talk, we'll basically talk for 8 hours about variants of this algorithm, okay, more or less. So, so you'll see a lot of it this week. But this is just to give you a preview of a taste. So there is a whole debate on whether this eta t should decay at 1 over t or it should decay at 1 over square root t, and it all depends. It's very subtle based on whether the function is strongly convex or not. So you will see lots of it. I mean, there's a whole bunch of issues there. Yep.
So where are the gradients?
These are the subgradients. So I'll show you that this is actually nothing but a gradient descent. So I'll show you that this is just the stochastic.
The gradient, even if you're on the right side, still the gradient is non-zero?
Yes, because you have a hinge loss. I'll show you in a minute. Huh? Again, I'll show you in a minute. If you have any questions about the algorithm itself, ask me. Maybe let me go ahead, and then maybe as questions come along, we'll answer them. Okay. So let's try to understand this algorithm. This sort of this guy is just showing me some weird algorithm at 10:30 in the morning, and I'm not even awake, and he's flashing things past me. What is he doing? Okay. So here, let's look at what are we trying to do, right? You have this objective function, and you're trying to minimize this objective function. Okay. So at the heart of this algorithm is the following approximation. So you say, at a time t, I'm going to take my objective function and approximate it by the following objective function, which is, I call this the instantaneous objective function, right? You can see there is an average here, there is no average here, okay? So this is just saying instantaneously, this is what this objective function looks like, okay? Now let me compute the subgradient. This is actually a simplified version of the subgradient, but this is enough for this algorithm. Let me compute the subgradient of this objective function, this instantaneous objective function. Okay. So the first question that was asked, why is this called stochastic? What is stochastic about this algorithm? The stochasticity is because of this approximation. Okay, so that's why it's a stochastic algorithm. It makes an instantaneous approximation to what you're trying to optimize. Okay, so that's why it's stochastic. Second question was, where is the subgradient in the algorithm? So I'll show you in a minute that this subgradient is used in the updates. Okay.
But when you say stochastic, I think something's going to be random every time you run it. It's going to give you a different answer. That's not what you're talking about.
Because I'm making an instantaneous approximation to the objective function, right? So which of course means that if data arrives in a different fashion, then I am going to give you a different solution. Yep.
Shouldn't you have the divergence, not just the Euclidean square of w, but w minus w log?
The divergence will come in just a minute. Yeah.
Would it not be more appropriate that you call this online gradient descent, because that's what you're doing, right? Instead of taking average.
So online and stochastic are very closely related. There is a little bit of confusion in people's minds. They think, oh, online algorithms are very different from stochastic algorithms. In fact, they are not. In my mind, if you want to really differentiate between the two, the only difference between them is stochastic gradient descent type algorithms assume that you already have the data in hand and you're just cycling through it many, many times, while online learning algorithms assume that you truly have streaming data, which means that once you see a data point, you never know whether you're ever going to see it again in your life. That's the only difference between the two, but they all work on this kind of instantaneous objective function. Okay.
Is your xt randomly chosen, like from the data?
Yeah, so I am assuming that this is just, there is some random oracle which is giving me my xt's. So it could be, for instance, that my xt's are coming by cycling through the data multiple times, and every time there could be a permutation that's happening. It's fine. Okay. So that's the only difference between this and an online algorithm, because in an online algorithm, you do not have control over the oracle. It just gives you data. Okay. Questions? Okay, good. Either I must be doing a good job, or I must be doing such a bad job that everybody is quiet. Either way, it's good. So if you look at this instantaneous objective, you can write the subgradient, right? It's a fairly elementary exercise. All you need to do is realize that if ytw.xt is strictly less than 1, then this part of the max is active. If this part of the max is active, then this is the gradient. Right? On the other hand, if it is not the case, then the max is active at 0, which means that doesn't contribute anything, and you just get this as your subgradient. Clear? So the subgradient part is clear to everybody. So now let's use this subgradient. Right? So let's take this subgradient. There is a name here, explicit update. We will talk about it. Just hold your horses for a minute. So this is your subgradient, and what you're doing is you take your previous solution, which is Wt, you have your step size eta t, and you have your subgradient. Okay? You just take a step in the subgradient direction. Okay? And this is your update. On the other hand, if this is bigger than or equal to 1, then your subgradient, this part doesn't exist, and you get a step which looks like this. Right? So if you go back here, what is happening is every time you're taking a step along the gradient direction, along the subgradient direction. Okay? And after doing taking the step, you're projecting onto a ball, because you know that the solution always lies in this ball. This is a special thing of the Pegasus algorithm. This itself is not so important. I mean, it has implications in the analysis, but in general people don't do this. This is just because they know that the solution lies in a certain space. So if you go out of that space, they project it back. They say, oh, I know that my solution lies here, why should I go outside this space? Right? So this is sort of a speciality of the Pegasus, but everything else is standard. Okay? Questions?
So is it wrong to think of this as when you're wrong, you try to get right and keep your weights small?
Yes. Yes.
And when you're right, you just try to keep your weights small.
Yeah. So basically, that's sort of the machine learning interpretation of it, is that you say, okay, if you cannot classify a point with a good enough margin, then you're penalized. Right? And if you know the perceptron algorithm simply says this is with a 0. Right? If you cannot classify a point, you're penalized. But here you're penalized even if you cannot get a good enough margin. On the other hand, if you get a reasonably good enough margin, you sort of say, oh, I'm just going to shrink my weight vector a little bit because I'm more and more confident. Yeah.
Yeah, but this update you can motivate if you go to the previous slide by adding a divergence to the last.
Yes, I'm going. That's in the next slide. Just wait for one slide. I'll come back to that. We will do this in great detail. Other questions? Right? So it's a really simple algorithm, right? All it says, let me make an instant. So at a high level, all it says, let me make a simple approximation to my objective function. Take a step along the negative subgradient direction and be done with it. And then let's do a projection. Okay? Then you must be wondering, oh, well, how do I actually motivate this update? Why does it make sense? Why should I be actually taking a step along the negative subgradient direction? Why is this the right thing to do? Right? So, and that's the question that's burning on Manfred's mind, and without letting him burst out with curiosity, let's try to motivate these updates, right? So how are we going to motivate these updates? This comes from a very fundamental principle in online learning, which says that as data comes along, you have these two minds. You're torn between these two objectives, right? On one hand, you say, oh, I really spent a lot of time learning my parameter vector W. I don't want to move too far away from it. I'm sort of tied to my previous parameter vector. Okay? On the other hand, I do want to minimize my objective function because I have some new information now. One more data point arrived. I have some more extra information. I need to somehow take that into account. Right? So here is, on one hand, I want to stay close to the previous W. On the other hand, I want that my objective function is minimized. Okay? And eta t is a trade-off parameter which says at what time, at time t, how much should I believe between these two things. Okay? This is the classic motivation. This is the same motivation that you use in boosting as well, and this is the, it's in countless many papers. But this is the sort of tension that you always have in online learning. Okay?
But say in a batch setting, batch learning setting, you can try multiple learning parameters for new t or what's
eta t.
But say in online learning, how can you decide on that?
So usually the eta t is tuned for the best rates. So you say, okay, if I want to have the best rates of convergence, so either you can talk about best rates of convergence or you can talk about something called regret. So you can say how well can I do as compared to a batch algorithm, and this is usually tuned. Okay, and that's where this, for instance, the Pegasus 1 over lambda t comes from tuning those rates.
But those tuning rates, are they derived from like some theoretical results?
Yes, they are.
Based on data?
No, they are derived from theoretical results. So you say, how can I, if this is my scheme, what is the best eta that I can choose in such a way that I can get the best rates of convergence. Okay, so that's what happens. Okay, so now if you do this, right, so you're torn between these two things and you minimize, so you say, okay, what I want to find is a W that is reasonably close to the previous one, but at the same time makes my instantaneous objective function small. Then you can write out your update in the following way. Okay? But pay close attention, there's something going on. Look at the terms highlighted in magenta, right? So again, this the rest of the 10 minutes are going to be reasonably theoretical. There is a lot of equations floating around, so please pay attention. I mean, if you're following, please, this is the time to stop your Facebook account. Okay? So look, there's something fundamental going on here. If you believe in this kind of an update, which is this classic online learning update, your Wt plus 1 depends on the gradient at Wt plus 1. Right? Manfred alluded to this before. It's kind of a chicken and egg problem. Where should I go depends on my gradient at where I want to go. Right? It is like if somebody asks you for directions to your house, you say, oh, well, my house is, is the place where I live. Sort of, it's a chicken and egg problem, right? So you haven't answered this question. I haven't answered your question. But usually the way people try to get over this problem is to say, let us do an approximation. Right? Since we are not going to move too far away, we know that we are reasonably close to Wt anyway. The gradient at Wt is not going to be too far away from the gradient at Wt plus 1. Let us do this approximation. Okay? And this is how you derive your updates. And this is exactly the Pegasus update. Right? This kind of an update is called an explicit update. Actually, Manfred coined the term. Was it in your 97 paper, the Kivinen Warmup? Yeah, I think it's in the there's a paper that he wrote, very influential paper that he wrote in 97, where he and Jyrki Kivinen coined the term and called this an explicit update. Okay? And as you can see, as I showed you, basically the Pegasus update is an explicit update. Okay? Now you say, well, can I do better? What if I'm really, really stubborn and I do not want to do an explicit update? I don't want that approximation. I don't like it. Can I do it? Right? Sort of seems hopeless, right? I mean, you're saying, oh, where you go depends on sort of the gradient at where you will be. So it's kind of funny business going on here. But it turns out that for some special cases, and this is where it's a beautiful part comes in, is that for some special cases, you can do this exactly. You can actually compute these updates. Okay? And this we figured out with a paper with Dale Schurmans and others in 2006. And it's a fascinating thing that we figured out. So let's see what happens. Okay? So you're saying, let us write the subgradient. Right? Let us write that subgradient of that beast that we are trying to optimize in the following way. So it's a slightly more compact way of writing it. So the way I write it is that the subgradient is lambda w minus some gamma times yt, and I introduce this gamma. And if your point is very well classified, right, then your gamma is 0. If your point is in margin error, then the gamma is 1. And then if it is exactly equal to 1, it is if you are at the kink of the hinge, then the gamma is between 0 and 1. Okay, so this is, you can sort of verify this. This is how you can write, this is the true expression for the subgradient, for the hinge loss. Okay. So now let us plug this back in there. Okay, so you get this expression. Okay, still not solved, nothing has been solved, right? You still are in the chicken and egg situation. Wt plus 1 depends on gamma, but gamma depends on what happens at Wt plus 1, right? So it's basically gamma is a function of Wt plus 1, but Wt plus 1 is a function of gamma. But before I show you how to break this chicken and egg situation, let me do a little bit of algebraic manipulation. So algebraic manipulation, nothing changed. Basically this is the condition that I want to satisfy. Okay, so Wt plus 1 depends on gamma. So the way I am going to do this is to cheat a little bit. Okay, so I am going to give you the solution and show you that the solution that I am giving you actually satisfies this condition. Okay, it turns out that for the hinge loss you can do it, for other losses it's a bit more iffy. Okay, for hinge loss and its variance you can do it, for other losses it looks a little bit more iffy. When we come back next time, I'll show you some very beautiful duality which also motivates it. Okay, so let us do the following thing. So what you want is to satisfy this condition, right? This equation. So what I'm going to do is I'm going to divide my situation into 3 different cases, and I'm going to show you that in all cases, if I did my update to Wt plus 1 or W in the right way, then sort of I would satisfy this condition. It's kind of cheating, right? So if your head is spinning by now, it should be, so you're normal, don't worry about it. But basically what I'm trying to show you is that there is a way to break this deadlock between Wt plus 1 and gamma. Okay. In this particular case, the way I'm going to break this deadlock is by giving you the solution. Okay. So I'm saying, suppose if Yt Wt xt is very well classified. So if this point is really well classified, okay, just take your weight vector, shrink it by a little bit, and use this. You can see that if you set Wt plus 1 to be this value, then Yt times Wt plus 1 xt is strictly larger than 1, right? You can verify this. And if it is strictly larger than 1, that implies that at Wt plus 1 the gamma must be equal to 0. Clear? But if gamma equals to 0, if you plug this in here, Wt plus 1 must have been written as 1 over eta t lambda plus Wt, which is what I wrote. So it's kind of, I am forward projecting and telling you the solution. Okay? This you can do only for the hinge loss. Okay? This is sort of special. Here is the second case. If your data point is not well classified at all, it's sort of really badly classified, then you should take sort of a full step towards the direction. Okay? And again, while the math itself is not important, I mean you can look it up in the slides. What is important again is that you can verify that if you took this step, then at Wt plus 1, Yt Wt plus 1 xt is strictly smaller than 1, which would imply that gamma at Wt plus 1 is equal to 1, which would imply that you should have done this update. Right? Sort of that's how I'm breaking my chicken and egg situation. Do you see it? Okay, by giving you the solution and then saying if you verify the solution at where I took the step, sort of it makes sense. Okay? And here is the third thing. Again, this is the math itself is not very important. Look it up. Okay? Now I want to summarize this update. So the summary is that my updates are going to, and these are called implicit updates, and the updates look like this, and I can rewrite this entire mess into this one nice looking equation. Okay? Keep this equation in mind. Okay, this equation will come back in a very different form, in a completely different motivation. This equation will come back. Okay, and I'll show you that. So how many of you have used lib_svm or liblinear here? So lib_svm, liblinear. Okay, so if you know liblinear, this is the equation that underlies liblinear. I will show you that next time. Okay, that's all we have for today. Thank you.